Okay, in this video I'd like to cover the third and final method for integration for this week in Calculus 2. The technique that I'm going to show you is actually an extension of a technique that we may have covered in college algebra, or you may have seen in college algebra. It's sometimes called partial fraction decomposition. And this is a way for us to solve rational functions in college algebra. But what we're going to do is the same or a similar technique here in order to separate an integral and separate it into two or more integrals and compute the composite integral by combining the results of the two separate integrals. Again, these are some videos that you may want to reference online. If you go to YouTube and type in or search for this little tag here, it is case sensitive, but that'll take you to a pair of videos that have other instructors' approach to this, and they do a pretty nice job as well. Now, the bottom line for the partial fraction decomposition is this. What we're looking for is a factorable polynomial in the denominator, and what I'd like to do is find the sum of two functions that equal this function so that I can actually find the integral of each function separately and sum those integral values together. So what I'm going to note here is that this denominator is factorable. It's a nice polynomial. So I'm going to leave the numerator alone for just a moment and determine the factors of the denominator. Now this one can be a little bit tricky at first. I think we all recognize that 2x times x is going to multiply to make 2x squared, and we might guess that 3 and 1 is the product that multiplies to make 3, which is good. In this order, 2x times 3 makes 6, and 1 times x makes 1. So if I had a negative 6 and a positive 1, that would lead us back to this center term. But this is actually an incorrect factor because now if I were to FOIL this back together, the positive 1 and the negative 3 would multiply to make negative 3. So we got to be real careful here. If I rearrange these numbers, put the 3 in this position and the 1 here, now if I report a negative 1 here and a negative 3, this outside product makes negative 2x, inside products makes negative 3x. We again arrive at an inner sum of negative 5x, but also our outer product becomes positive 3. So there's a good factored denominator. So from here we're going to follow what I like to call the cover-up method. There's basically 3 steps to it. Now that we have factors in the denominator, we're going to determine the zeros of each factor. And once we've done that, we're going to cover up the factors one at a time and substitute in the 0 that we found in step 1. We'll do that several times. And then finally in step 3, we're going to simplify each of these expressions to obtain our new numerators, if you will. So the rules standing alone can be a bit vague, so what I'm going to do is try to run through a couple examples here. I'm going to use this black ink to represent me covering up this factor. Actually, before I cover up that factor, let's find out what the 0 is. So the 0 of this factor is going to be 3 halves, right? So 2 times 3 halves minus 3 would be 0. So I'm going to cover up that factor now, and I'm going to substitute in 3 halves into the remaining expression. So I'm just going to do some side work here, and I'm running out of room, so I'm just going to place it here. I'm going to call this value my a value. If I had 3 halves minus 5, and I had 3 halves minus 1, the simplification of this expression will represent a new numerator that we're going to use in just a moment. So I might call this 3 halves minus 10 halves and 3 halves minus 2 halves, just to make the math a little bit easier. This looks like negative 7 halves over 1 half, positive 1 half. Those 2's will cancel, and this a value ends up being negative 7. I'm going to do the same for a b value, and I'll do that by covering up the other factor. Now the 0 of this factor is going to be positive 1. So when I cover up this factor and we make the substitution, I need 1 minus 5 in the numerator, and the remaining factor is 2 times 1 minus 3. So this looks like, to me, what do we get? A negative 4, and 2 times 1 is 2 minus 3 is negative 1. So the b value is 4. All right, so I don't have a great explanation as to why this technique works. I haven't sat down and considered all of the algebra that works out here. But effectively what we're able to do now is we're able to recreate the sum of two integrals in the form of two separate fractions. So let me uncover this one and we can see exactly what we're working with. So this a value that was obtained becomes the new numerator of a fraction over top of the factor that was used to obtain it, over 2x minus 3. And the b value that we obtained, 4, becomes the new numerator over the fraction of the second factor that we used to obtain it. And now we've decomposed this original fraction into two separate fractions whose integrals are much easier to determine. Now it may seem strange what we've just done, but as a side note and as an anecdote here, we can show that the sum of these two fractions really is the same as the original function. So let's go ahead and do that. If you recall, to sum these two functions together, we need a common denominator. So I'm going to multiply the left side fraction by x minus 1 in the numerator and the denominator. And I'm going to multiply the right side fraction by 2x minus 3 in both the numerator and denominator. Now, since these have a common denominator of 2x minus 3 times x minus 1, the numerators could be combined together. After distribution, this is what we get. And finally, after combining like terms in the numerator and multiplying the factors in the denominator, we end up with this fraction, which is indeed the same as the fraction that we started the problem with. So it's kind of an interesting method, a way for us to separate into two individual fractions that are easier to integrate, and we'll continue to proceed from here. So I'm just going to remind myself that the integral of 1 over x dx is equal to the natural log of the absolute value of x. We just need to make sure that x remains positive. So if I'm remembering this rule here, then integrating these two functions should be fairly straightforward. I'm going to push this -7 constant out front, and I'm going to imagine this is 1 over 2x minus 3 dx. So the antiderivative of 1 over 2x minus 3 is going to be the natural log of the absolute value of 2x minus 3. But again, because of this coefficient, we've got to offset that. So I'm going to multiply this by 1/2 as well, plus c, although I'm going to remove that for just a moment. When we complete the same process over here, we can factor out a 4, and we're left with 1 over x minus 1 dx, and 4 times, again, the antiderivative of 1 over x minus 1 is going to be the natural log of x minus 1, absolute value, and I'll include my plus c at the end here. No need for a multiplier offset here because the coefficient in front of this x is just 1. And so this looks like a pretty good answer. Perhaps we can clean it up just a little bit here. -7/2 natural log of 2x minus 3 plus 4 natural log of x minus 1 plus c. And I think that would be a pretty good final result. Now we can apply the same technique to this example over here. Fortunately for us, it looks like we had a cubic polynomial that's been factored already. So if I were to use the cover-up trick where I cover up this one, then this one, and then this one separately, let's see what we can get. I'm going to identify a, b, and c values this time. We're going to separate this into 3 fractions. Now the value that's going to zero out this factor is going to be 1. So if I had 2 times 1 minus 1, I'd have to write that as a fraction over 1 minus 2 times 1 minus 3, because we're going to sub in each x for the value that made that 0. For my b value, we'll cover up this middle fraction, or I'm sorry, middle factor, and that 0 was 2, so we've got 2 times 2 minus 1 over 2 minus 1 times 2 minus 3. And then when we cover up this third factor, 3 is the 0 there, so I need 2 times 3 minus 1 over 3 minus 1 times 3 minus 2. And in each of these cases, you can take the time to simplify them on your own. But in the interest of time, I'm just going to show the solutions here. I think for A, we end up getting 1/2. For B, we get -3. And for C, we get 5/2. This is based on work that I've done earlier, and I didn't double check these, so if you have the time, please check these on your own to verify that we've done the work correctly. Now, having these 3 new numerators, we're able to rewrite our antiderivative in a separate way, or in a slightly different form. So we'll kind of jump from here down to here now. We've got an integral of 1/2 over x minus 1 dx plus the integral of -3 over x minus 2 dx plus the integral of 5/2 over x minus 3 dx. Each of these denominators is really nice to integrate because the coefficients are just 1. So it looks to me like we're going to have 1/2 natural log of the absolute value of x minus 1 plus, well, let's call it minus 3 times the natural log of x minus 2 and plus 5/2 natural log of x minus 3. And we'll try to squeeze in the plus c at the end. So again, this technique is really just an extension of our college algebra class. The partial fractions method is really a decomposition method for rational functions, but it does provide a helpful tool for us here in calculus. So I hope this video helps explain that technique, gives you a couple extra problems for practice. If you have questions, please let me know, and I'll see you in class. Thanks for watching.